All right, so let's look at the um the case whereby we have slabs, or let's look at slab design for continuous slab spanning in two directions, okay? Uh, which is one of the most common types of slab designs you'll find doing. Um, so let me just have that in here. So let's see, slab design. Uh, so let's say for continuous. All right. In two directions. Okay. So this is I find this again common with most design processes. Uh, just gonna bring it up. So I'm gonna bring this panel. One of the important things we looked at in the previous discussions. It's gonna bring it up again just as a refresher. Okay. So when we are looking at continuous or slab spanning in two directions, all right. So for example, if you look at let me change the color. So if you look at P3, uh, P6, P5, P8, P11, P10, and P7. All right. With a particular focus on P7, P8, and P9, you'll see that the the slabs are continuous over the beams, right? So let's say if this is let's say beam one. No, this is beam one, sorry. Let's make this one beam two. This is beam three. This is beam four. Okay. So maybe let me call this one beam beam X. Maybe this is beam Y. All right. So you can see that the panels P7, P8, P3, P9, sorry, they are continuous over the supports. All right. So because of that, I think I mentioned that we can have either discontinuous support or continuous support. All right. The continuous support are typically the support at the ends of the slab, which are normally simply supported. Okay. So if we take panel 7, so let's start with panel 7. So I'm just redrawing panel 7. Let me call this P7. Now, because there's a void over here, all right, the beam here is what I'll call a discontinuous beam. So the beam, which is the beam BY is discontinuous because of the void up there. Now, if you look at B1, so this is let me just name them nicely. Uh, this is our BY, and then if you come to the beam on the side, okay, this one is our beam B2. Because there's another panel on the right, which is panel 8, it makes this support a continuous support. All right. Now, if you look at B1, there's nothing on the left of B1. So again, this will be discontinuous. So this is B1. Now, if you look at BX, so BX, so this is BX, okay, will be continuous because of the panel P10. Okay. So a typical um, slab of this nature, uh, I think I forgot to mention, but usually these are what you call the edges. All right. So these are the edges of a slab, all right, or of a slab panel. Okay. So if these are the edges, and then let's assume that BY and then B1 are simply supported. Okay. So because of that assumption, we can then looking for a table to show you. I think it's in the code. That'll be table 3.1, I think 3.13 and 3.14. Okay, all right. So these are typically what you call, they can be interior panels or exterior panels or whatever. So when you have two, so yeah, let me again mention this. So I have here my LX. Okay, let me call this LX. Let me call this LY. Okay, so LY is more than LX. So that makes this one the shorter span, and it makes LY the longer span. I'll bring up a table which I think will be of use to us. Let me see. Well, how can I bring this table? Uh, can I extract? Let me see. Um, yes, print that particular page. Uh, page. Okay. Because then this table becomes helpful to us in trying to understand some of these information that we need. Okay, so let me just bring that one down here. I'll try and add that to your lecture notes so that you can have access to this table, since it will be useful to us. Okay, so this table, this is a very important table, and this table helps us to know which panels to deal with, all right? So here, with this particular, if you look at this, the panel 7 has two discontinuous edges, all right? One long and one short, all right? And they are adjacent to each other. So that will be this panel, okay? So when designing, this panel is what we'll look at, okay? Where you have two adjacent edges discontinuous, okay? So that's for panel 7. Now let's look at another panel, okay? Just so that we have a grasp of what is happening and how to go about some of these. So for now, I'm just trying to explain to us, um, I mean, how to go into the table and then pick information from the table. Okay. So now let's look at panel 8. All right. So with panel 8, just like how we had panel 7. Okay. So panel 8, these sides are all continuous. This is also continuous. Here is also continuous. All right. but then this space here is discontinuous. Okay, so here our red means discontinuous, and then our blue means continuous. All right, and here our LX is so here what it means that this is shorter edge discontinuous. So it means that when you're trying to analyze panel 8, the data that you pick from for panel 8 would be based on the type of panel, and that will be one short edge discontinuous. So it would be this for panel 8. Okay. Um, with panel 9, so the same idea is going to be worked on. So with panel 9, let's see how it goes. This end on the left of it is continuous. The top here is also continuous. The bottom here is also continuous. And assuming that B4 is simply supported, all right, assuming it's a simple support, then it means that, so we'll have, so for um, panel 9, so let me just put this over here so that, so panel 9, we have longer edge continuous. Sorry, discontinuous. Okay. So again, you have to come into this table, and this will be the panel you work with, B9. Okay. So we have what you call the interior panels. So I just want to explain the rest to us. So the interior panels will come into play when all the sides have uh, are continuous over supports. Okay. So then this will be a typical interior panel. All right. Then we have two short edges discontinuous. An example would be, I don't have one over here, so I don't have that example over here. All right. But usually what's going to happen is that um, for the two short edges discontinuous to happen, then it means that these two sections, the shorter spans, will typically be simply supported, and then the longer spans would have um, or will be continuous over the support. So this is for this right here. Then the two long edges discontinuous is just the vice versa. I mean, switching places for the two of them. Then we have three edges continuous. So three edges discontinuous. And in this case, one long edge continuous. Let's see if I have an example. Again, I don't have any over here uh, to show it to you, but usually this is how it's going to look like. Let me just go ahead and draw for the two. Okay. So let's say three edges discontinuous. So we end up with something like this. And then here, okay. So here, if one of the long edges is continuous, then there's an option that we go with. And then here, if one of the short edges is continuous, while the rest are discontinuous, we go with that option. Okay. So this is what we have. And it depends on the kind of paddle system that you have. All right. So generally, when it comes to trying to solve these types of problems, we need to figure out which types, I mean, what panel type are we dealing with? All right. Then from there, we can do our uh, design based on that. All right. So let's look at basically what goes into the panel design process. I'm looking for a rectangle. Okay. Let's say I have a panel like this. Okay. Let me make it black. All right, great. This looks too far. Okay. Let's say I have a panel like that. Okay. Let me call this length. Doesn't really matter. Let me call this length Ly. Right. Ly is just the longer length, and then Ls is the shorter length. But nothing to do with orientation. Okay. All right. So usually when you have a continuous slab, what it simply means that you have some moments and the supports. Okay. So there'll be some moments acting as the supports. In addition to the moment at the midspan. Okay. That's supposed to be your MSX and your MSY. All right. So what we do when it comes to cases like this, we we try to divide our uh, what's the name? Divide our slab into slabs that have what we call strips. All right. So we use the strip approach to design these types of sorry, excuse me. So we divide. So here, uh, so this is like a slab panel. So we look at division of put over here, division of slab into strips. Okay, and typically there are two of them. We look at the middle and then the edge strips. So let's look at the two and then how they would help us to solve our problem. Okay, so let me just draw. Okay, something is not right. All right, so I think we are back in business. So we have, let's say we have these two. So I'm gonna draw the next one here too. So I think this should be fine. So if you are dealing with the shorter, um, or let's say if you are dealing with span X, uh, so let me put this right here for span LX. This is for span LY for span LX. These are the strips. So we have the edge strip, and then we have the middle strip. Okay. So the distances for the edge strip, it is 3/4. No, 3/4 is in the middle. Sorry, it's L over, it's 1/8. Okay. don't know what's happening to my eraser. So it's not erasing. Okay, great. So this one becomes uh, Ly over 8. Here's also Ly over 8. Then in between here is 3 over 4 Ly. So this is for span Lx. Then for span Ly, these are your strips. Okay. So again, these will be your measurements. So this will give us what's the name? Lx over 8. This is 3 over 4 Lx. This is Lx over 8. Okay. So here's your middle strip. Okay. And then here you have your edge. Here you have your edge strip. Okay. So again, middle strip. Then here is your edge strip. All right. So this is to take into account the fact that we have moments happening at key locations. We have moments happening within the span. All right. The span of the slab. They also have moment acting around the supports of the slab, right? And these moments are bi-directional, one in the X direction, and then one in the Y direction. Okay. Um, so we'll see how all of these things will play out. All right. So we usually use this edge strip and middle strip and all of that, usually when we have the case what's the name? When we are looking at usually if the edge is discontinuous because there should be some amount of reinforcement in that zone, and usually we use a nominal reinforcement. All right. Um, so let's see. Just going up to bring up some information. So when we're looking at the analysis of the simply supported two-way panel, we we have the moment just like that. We have the moment also in a bi-directional mode. So we have our um, MSX. Okay. But this time around, since we're looking at continuous, we use the uh, the moment coefficients beta Sx and then times the load, the ultimate load n times the length of the shorter span x squared. Then our mxy will also be beta xy dot n dot lx squared. Okay. So this is for finding the moment, all right? And we'll get to see that this moment msx, we can have positive moments, which is usually in the span or the middle strip. Then we can have negative moment at the supports. So for each moment, we'll have, let's say, for example, for MSX, we can have MSXP and also have MSXN, where N stands for negative. So this is for negative. So this normally will be at the supports. Okay. And this will be at the spans or in the spans. Okay. So let's look at an example. I mean, to appreciate what is happening, uh, to explain things a bit further. So let me pull up a drawing which should be useful to us. Where are you? Okay, so I just brought up this figure, and that should guide us. Let me reduce this a little bit. Okay, great. So we have this panel, or this sets of panels, right? And this, so let me just put some information here. This shows an office floor. Okay. Uh, let's say first floor, for example. Okay. So with this office floor, so let's say with individual, let me add that to it. Individual panels. Continuous over two or more supports. Okay. So the imposed load for this particular floor is, so let's say the loads, our live load is, let's say, 4 kilonewtons per meter squared. And then finishes plus ceiling will be equal to 1.25 kilonewtons per meter squared. Then the FCU, which is the characteristic concrete strength, is, let's say, 30 newtons per millimeter squared. And then that of the steel reinforcements, let's say, is maybe 460 newtons per millimeter squared. All right. So we have all of that information. Again, let's see the cover to reinforcement is, let's say, 25 millimeters. Okay, all right. Yeah. So let's look at what to do. So let's calculate. We will look at it, calculate the midspan. Midspan moment for panels. We have two panels to look at, panel A, B, 2, 3, and then panels B, C, 1, 2. So now let's go look at what these panels are. Let's just shade them. So panels A, B, 2, 3 will be this panel right here. Okay, A, B, 2, 3. So this is the panel, this is the first panel. Okay. Again, these are the outline. So this is the outline of the, so this is the outline of your slab. All right. Okay. So that now help you to know which part is continuous or discontinuous. All right. Now let's look at panel BC1, 2. Panel BC1, 2 be this panel right here. Okay. So at least we know what we have. Okay. All right. Please take a note. The slab continues towards this direction. All right. Continues as well. I mean, because there are no outline, it's good. We are just showing a part of the slab. All right. Even though it goes all the way to the right, we're just showing a part of it. Now, all right. So let's do this. So let's uh, assume floor thickness to be equal to 180 millimeters. So let's start looking at what to do with this information. So let's find out if it's so let's look at the solution. Let's look at Ly over Lx. Okay, so now we are looking at okay, let me just do it this way. We are looking at this panel A, B, 2, 3. So Ly over Lx would be if we go up here, so the Ly will be the longer length, which is 7 meters, and then the Lx will be the shorter length, which is 3.75 meters. Okay. So 7 over 3.75 would give us the 1.867 more meters, right? So this one is less than 2, so it makes this hence two-way. All right, or two directions. So two-way slab. Okay, great. So once we have that, uh, I forgot to deal with the loads. Let's just deal with the loads. So with the loads, okay, let's find the total dead load. Okay, dead load will be equal to, or before that, let's find the load from the self weight. So the self weight of the slab. Okay, so this is going to be the unit weight of the slab, which is 24 kilonewtons per meter cube. This you can get from BS 649. Okay, and then times the thickness of the slab, which is 0.18 meters. So when you do these calculations, um, what would that give us? Uh, do I have the information somewhere? Uh, okay, so 24, this will give us 4.32 kilonewton per meter squared. All right. So our total dead load in this case will be that of the finishes and ceilings, which is 1.25 plus the 4.32, and that would give us, I think, 5.57 kilonewtons per meter squared. Then we know our live load to be 4 kilonewtons per meter squared. So the N, which is our ultimate design load, all right, will be 1.4 GK plus 1.6 QK. So 1.4, our GK is 5.57 plus 1.6 times our QK of 4. And this will give us 14.2 kilonewtons per meter squared. All right. So now we know our N. We can look at our calculations. All right. Which one am I solving first? Oh, sorry. AB. I'm solving the AB 2, 3, not the A, not the B. Sorry. So then this one, let's go back. Let's correct it. This is supposed to be over 5. All right. So 7 over 5 rather. But it's still gonna be this is 1.4, which is less than 2 anyway, so it's still fine. All right. And then let's see what that panel has for us in terms of whether it is continuous or discontinuous or otherwise. So we go in here. Okay. So we know that this length is supposed to be our 7 meters. And this length is supposed to be our 5 meters, right? Okay. So going back to the yellow shaded region, it means that this, let me use a different color. This end here is discontinued because That is the edge of the floor. So that edge is discontinuous. So what it simply means is that to use the same color coding, this edge is discontinuous. And then, oops, these edges are continuous. Okay. So it means that here I can say that one long edge discontinuous. Let me put over here. All right, so one long edge discontinuous. Okay, so when that happens, it means that the coefficient for the moment, you go back, you go to your table and pick that information. All right, what's wrong with my screen again? All right, so you come here and then you come in here, look for one long edge discontinuous, and that is very similar to that of the P9 that we had. All right, so we need our BSX or beta SX. So beta XX for one long edge discontinuous, what we are focusing on is the mid-span moment. All right. The mid-span moment with our LX, LY over LX being 1.4, then our mid-span moment is 0.051. Okay. So 0.0, because that's what we're being asked to find. Find the mid-span moments, right? So I can write in here that BXX is 0.051. Okay, so that's for the moment uh, for the short span for the mid span as well. All right, so this is 0.051. Now let's find BSY. Again, these are for the mid-span moments. Please take note, mid-span moments, not support moments. So these are the mid-span moments. So we go back to our table as we had it, and then our BSY will be this value regardless of our LY over LX ratio, right? Doesn't really matter. Okay. So this is 0.028. So BXY will be 0.028. So now our MSX will be equal to BXX and LX squared. So that would be 0.051 times an N value of 14.2. Then our LX in this case, here our LX is 5 meters. So it becomes 5 squared, and this will give us 18.1 kilonewtons meter. Okay. So this is a mid-span moment in a short span. Okay. Then a mid-span moment in the long span will be B beta SY and LX squared. So that will be 0.028 times 14.2 times 5 squared. So this will be 9.9 kilonewton meter. Okay. So these are the moments, all right. So normally, let me put this one here as an aside. Okay. So from here, you can find um your K values, all right? Then you find your corresponding, so you find, let's say, KX, KY for the different K values. Then also find your corresponding AXX and then AXY from here. All right, then you can use that to pick the rebar size and then all of that. Okay. Now let's look at the other panel, the panel BC12. So panel BC12. That one, your LX, again, going up, our LX is 3.75, BC12, yeah. Our LX is 3.75, and then our LY is 7 meters. Uh, so this is 3.75 meters. Okay. So our Ly over Lx will be 7 over 3.75. This should give us, I think 1.87 as I had earlier. And this is again less than 2, so we're good to go. Right, now let's take that same shape. Let's draw the shape again and then see which part of it is continuous and which part is discontinuous, right? So going, you would realize that these two edges are discontinuous. Okay. And then the other two edges here are continuous. Okay. So I can say two adjacent edges discontinuous. So again, that would inform us as to what to do with the information from the table. So again, you can just say again, go to table 3, I think it's 3.14, right? So we go to the table above, and then we pick our values for BSX and then BSY. All right. Okay. So we go back to this table, once again. Let's go slowly. Yeah. So we got what, 1 point, I think Ly over Lx was 1.87. So somewhere in between. So it's somewhere in between here. All right. And then we are looking at two adjacent edges discontinuous. So we will focus on this value right here. Again, it's midspan moment. All right. So you can do your interpolation, and then you check these two values and then see which ones would work. I mean, do the interpolation and you find some value in between the two. All right. So this in between the two, you get our BXX, and then this will be our BXY. Okay. All right. So with regards to interpolation, if you do our interpolation, our BSX would be 0.0675, and our BSY will be 0.034. And once we have these, we can find our MSX. So our MSX would be 0.675, which is our beta SX, times our N, which is 14.2, times our LX, and this is 3.75 squared, and they should give us 13.5 kilonewton meter. Now MXY will be 0.034 times again 14.2 times 3.75 squared, and this then will give us 6.8 kilonewton meter. Right. So here we are just going through the motions to understand what goes into how to calculate the moments. All right. Okay. Let's look at some more examples just so that we appreciate what we have. So now let me call this one II. So again, on the same example, now let's say design the steel reinforcements. So the same thing, now we are doing some bit of design. All right. Reinforcements for panel, let's say BC23. Okay. And then it says check the adequacy, okay, of slab in terms of shear and deflection. Maybe I can touch on deflection a bit more, okay? Then it says illustrates the reinforcement details. Let me say let me just write reinforcement. Okay, great. So now let's look at so we are looking at panel BC23. Let's go let's go look at panel BC23. So I think this is supposed to be the shaded portion over here. All right, BC23. So let's design it. All right. If you look at panel BC23, you will see that it is continuous on all sides. All right. So because it is continuous on all sides, we call that an interior panel. All right. So let me just redraw and then state that. Oops. I want black. For whatever reason, it's not working. Okay, let me just redraw. Choose my color. Okay, great. So it is continuous. Oops. So it is continuous on all sides. So no red in here. Everything is blue. Okay. So because it's continuous on all sides, this becomes what we call an interior panel. So with that, this is our Ly. This is our Lx. All right. So Ly over Lx will be 7 over, I think, 5. So this will be 1.4. Okay. And since we are designing this particular panel, it means that we have to find the moment at mid-span and also find the moment at the supports. All right. So we'll have 4 different calculations. Okay. So let's find PXXP. So let me call it that. So this will be So this will be the short span um, coefficient for mid-span moment. Okay, for the mid-span moment. Okay, and typically we call this the positive or the sagging moment. Okay. Then we also have so beta SX and this again will be this also be the short span moment, but then it will be the short span moment for the continuous edge. Okay. So it will be the short span moment for the continuous edge. So let me just short span moment for uh, continuous edge. Okay. And this is what we call the negative or the sagging moment. Sorry, negative or hugging moment. So you have BSX, P positive, and BSX and negative. Okay. So in the same way, we also have what? B. So we also have what's it in BSX. So BSY positive and then BSY negative. All right. So that's like that. So then this will be for the long span coefficient and then the long span coefficient for mid span and then continuous edge, respectively. All right. So let's look at these let's look at how to get these values. Um, so BXP would be beta XX and would also be and beta SY positive would be the beta XY negative would also be. So now let's go to the table and find these values. Okay. So this table is very important to us. So here we are focusing on an interior panel. So we will be looking at this zone. Um, so we'll be looking at this zone right here. And so here, this is our BSX uh, negative, and this value here is our BXX positive. All right, since our ratio is 1.4. Okay. Then when you come in here, this is our BSY negative, and this is our BXY positive. All right, so these will be our values, and then we'll use this to determine the moments. All right. So let me just rewrite them down here in the solutions below. So my BXX negative, I think was 0.05. I'll have to go back and check it. And then BX positive was 0.037. And then BSY negative was 0.032. And BSY, why do I keep saying B? Please, it's beta, not B. Beta SY positive is 0.024. Let me just make sure I got it correct. So 0.05 negative, 0.037, 0.024, and 0.032. All right, so I think I'm good. Okay, so now let's find the moments. All right, so the moments will correspond the coefficients. Okay, so with the moments, I'll have MSX positive, which will be 0.037 times the load, which is 14.2 times here, our LX is 5 meters, so 5 squared, and that will give us 17.8 kilonewton meter, sorry. So this is supposed to be uh, short span, short span, mid span moment. All right, so that's what this is for. All right, then let's look at our MSX negative. That'll be 0.05 times, again, 14.2 times 5 squared, and that should be, no, this is not 17.8, this should be 13.1, I believe. Am I correct? Okay, yeah. So this will be 17.8 kilonewton meter. Okay. And this is the short span continuous edge moment. All right. So we keep doing same thing. Our MSYP will then be 0.024 times 14.2 times 5 squared. And that would be 8.5. So it becomes a bit repetitive going forward. You keep doing the same things again and again. And all right. So just keep repeating. And then this will be, I can just copy the information here. Uh, uh, this is crazy. My, all right. So let me make a copy. Sometimes it's just not good to be lazy, but oh. Okay, so this will be the long span, not the short span. So let me just do the correction. This is a long or longer span. All right. So these are the things that we need to take note of. And then let's look at, so once you get your moments, the next things will be to design the what's the name? So basically, when it comes to the reinforcement, okay, uh, just know that in this case, at the support, okay, and this is um, peculiar for this case, for this particular slab. For other slabs, it might be different. So at the support, the slab is going to resist hugging moments. The slab is resisting hugging moments in both the short span, in both short and long span directions. Okay, just take a note of that. It's not always the case. All right. So in the same way, when we are designing a slab, it just means that we'll have uh, on the, I think, let me just draw that so we see what's happening. So if this is like the section of the slab, you will have rebars at both. So you have what's the name? Two layers of rebar, okay, at the top, and also two layers of rebar at the bottom. Okay. So typically this will be rebar arrangements coming from MSXP. All right, and this will come from MXYP. All right, and then here, here you have this one will be your MXX negative, and then this one will be MXY negative. Right. So no, what's going to happen is that means that you have to note that the D values, the effective depth values will change. The effective depth values will vary. Okay. So this is like how we had a doubly reinforced beams, something very similar, right? Doubly reinforced. So this one becomes like a doubly reinforced um, slab in the way. All right. So take note. Uh, the effective depth will vary. Now let's look at what did the questions say? Let's go back to the question. What did it say? We should design a steel reinforcement for this particular all right. So let's look at for the design, let's look at our MX. Let's see. So let's look at the for the mid span. Okay. So for the mid span, our MSXP was giving us a 13.1 kilonewton meter. All right. Uh, let's calculate our effective depth. All right. So D will be equal to H, which is our height, minus 5/2, which is the width of the diameter of the rebar, minus C, which is the cover, and that will be 180. Let's assume that phi is 10. Let's say I'm using 10 mm, okay, for the rebar. So it becomes 10/2 minus 25, and this should give us 150 millimeters, okay? So this becomes the D, all right? So MSXP. Now our ASXP will be equal to, what's the name? The moment MXP over 0.87 FYZ. Okay, and this is going to be 13.1 times 10 exponent 6 divided by 0.87 times 460 for the FY, and then for the Z will be 0.95 times 150. Okay, we have already established that in previous calculations. So what will we get? I mean, you can find K and all of that is fine. So this should give us 30.1, 10 exponent 6 divided by 0.87 times 460 times 0.95 times 150. Okay. So this will give us 229.7 millimeter squared per meter. Okay. And always check if this is more than your AS minimum. Okay. And since we are using a 460 M bar. Our AS minimum is 0.0013 VH. All right. Okay, and this is I think our B will be 1,000. So let's check and see. So it becomes 0.0013 times 1,000 times an H of 180. And this will give us 234 millimeter squared per meter. So we can see that, oops, AS minimum is more than our ASP. So we choose the AS minimum, all right? So with that, we would normally go to this table. Let me just go back. Let me copy through this process rather. It's easier that way. Um, so we use, so we go to our cross-sectional area. So in this case, this is, we go with the 234. And since we are looking at bar size of 10 millimeters, 234, the lowest we can use in this case will be 262. All right, so I can say that, okay, provide T10 at 300 millimeter centers, whereby our AS provided will be 262 millimeter squared per meter. So that will be this guy right here. Okay, and then this will be our spacing. So that's how we design the MSP. And this is basically, we call the bar in the shorter span the main bar or the main. So some will say this is the main steel. So let me put it this here rather. So that it's actually here. Okay. So we are still on the mid span. So we are still on the mid span. Okay. So we have the mid span A where we are looking at the main steel. Then the mid span B will be what we call the secondary. So with that one, we know our MX, so that becomes MSYP. So MXYP is 8.5 kilonewton meter. We need to find a D for that, okay? And this is the best way to explain this, all right? Since you already have this bar here is the main bar or the main steel, okay? And then we have here the secondary. So this is the secondary. So initially we got a D for which was the 150. Now we need to find another D where that D will be for the secondary. Okay. So this is the D for the secondary. Maybe let me call that D prime so that we differentiate between the two. So let's call that D prime. And then maybe just so that it helps us to appreciate what is happening. So D prime here in simple terms would be H minus the phi. So this one is phi of the main rebar minus phi of the secondary rebar over 2, then minus the cover. Okay. So when you do the math, it becomes 180 minus 10 over 2 minus 25, and that'll give me 140 millimeters. Okay. So with that, I can find my AS, let's say ASYP, just so that And that'll give me so that'll give me what uh MXYP over 0.87 times FYZ. Okay, so this becomes 8.5 times 10 exponent 6 divided by 0.87 times 460 times 0.95 times 140. Okay, so let's look at what that will give us. 8.5. So you can see that they keep repeating, and this will give us 159 millimeter squared. Let me put a point. 159.7. So that's roughly about, let's see. So let's say 160 is 5 millimeter squared per meter. All right. And again here, our AS minimum, which is 234 millimeter squared per meter, is more than what we had. So we go with the AS minimum, which means that we'll end up with the same calculations as we had previously. So I can say provide T10 again at 300 millimeter centers, where our AS provided will be 262, I believe, millimeter squared per meter. So this will be in the long direction, okay? Whilst the other one will be in the short direction. Let me just add that so that at least it helps us to, when reviewing, it's easier. Okay. Um, okay, so that we'll do for the what's the word? Uh, so for the support, so now we've done the mid span. The next is to look at the supports. So the support, we also have main. So for the supports, we'll have A, which is the main STU, and then we also look at the what's the name? Also look at uh, the secondary, right? Then from there we can draw the shape of the, the rebar detailing. All right, so let's look at the main steels for the what's the name, for the top, the supports. All right. Um, so I think with that one, so that would be MXXN, and we got that to be 17.8 kilonewton meter. Again, if I'm to draw to help us to appreciate what is happening again, this is the rebar arrangement. All right. So this will be the top, the main rebar at the top. This is not the best way to draw it. So this will be the main rebar at the top. All right. And then we have the secondary bars just below. All right. So with that in mind, it means that we can find the D values just like what we did. So for what's the name? For what we did with regards to the midspan calculations. All right. All right. So let's see how that so in effect the D and the D prime would be the same for that of the main bar. All right. Okay, great. So pretty much it means that this distance here is my D, and this distance here is a D prime. All right. So here our D will be 150 millimeters. Okay. You can check K and all of that and see. Uh, all right. So like normally it's a good practice to always check K. All right. Check K and then compare if K is small. I mean the value of K then should help us to calculate Z. Okay. All right. And then we'll compare if Z is more than 0.95D. Right. If it's more than 0.95D, we use 0.95D. Okay. We usually do that for our calculations. All right. So that's what basically I've been trying to work towards. Okay. So now our ASX negative will be the 17.8 times 10 exponent 6 divided by 0.87 times 460 times 0.95 times 150. Okay. So if we do these calculations, we should also have some answer uh, for our, what's the name? So 0.87 times 460 times 0.95 times 150. And this will give us 312, I believe, if I'm correct. 312 point, oh, 312 is fine, millimeter squared per meter. And this, our AS minimum, I think, was 234 millimeter squared per meter. So we go with the bigger value, all right? So again, we go back to our table that we had, and let's go with this option. So again, with the 10 mm, we got 312, so we can choose 314, which works. Okay. So um, so let's say we can write provide. So I can do provide T10 at 250 millimeter centers, where our ASP on the area, some will say AS, which is the area provided, would be 314 millimeter squared per meter. Okay. And this is again in the short span. Okay. All right. The next thing will be to do for the secondary. So the A is the main, and then B is the secondary. Okay, so we do for the secondary. Secondary steel. Let me just highlight them so that at least we know what they are. So for the secondary, our MSY negative is 11.4 kilonewton meter. All right. And our D prime would then be 140 millimeters. Okay. So again, you can find your K, find your Z value and all of that. Okay. So our ASY negative will be 11.4 times 10 exponent 6 divided by 0.87 times 460 times 0.95 times 140. Okay. So 11.4. So this should give us 214, I believe. Yeah. something close to that. Okay. So we get 214 millimeter squared per meter. But again, we will see that our AS minimum, which is 234 millimeter squared per meter, is more. So we go with that. So it will work almost the same as that of the other two that we calculated for. Okay. So here our AS is, I think we had 262. Okay. So we have done, so for this panel, these will be our sets of calculations for for that of the what was her name? That of the panel, the panel that we've been looking at, panel what? Panel BC23. Okay. Now let's check shear. I didn't really state anything on shear earlier, so I'm just gonna use this opportunity to highlight shear as well. When it comes to shear design, so let me just write here, shear. Okay. So we also have a table which we can use to do shear design, and the shear for or the maximum shear force V SX is equal to a coefficient for the shear uh, beta Vy times NLX. Sorry, beta Vx. All right, and then the shear in the y direction, or sorry, shear in the long span at the support will be beta BVY and LX. All right. So this is so this is shear force. Oops, trying to reduce the thickness. Okay. So this is shear force at support for the short span. Okay. So this will be the shear force or the design shear force. All right. So just say design shear force at support for the long span. Okay. So again, we have, if you go to table, so if you use table 3.14 in the code, it has all these properties for us. Let me see if I can pull that table. Okay, so let me just get the table and then I can add that to the work and then we'll look at it. All right. So this is shear coefficient. Uh, are you? So it should appear in a moment from now. Let me just take it up. So this is a shear table. It works pretty much the same as that of the bending coefficients table, right? Nothing strange, pretty much the same approach in terms of picking up these coefficient values to do our calculations, all right? So let's see how to go about that with regards to what we are doing. So with shear, if you take this table, let's again, we are looking at interior support. Do we have interior here? Four edges continuous. Okay, so that's supposed to be interior. All right. So these are interior, four edges continuous. And then so we focus on these two values. All right. So beta Vy and then beta Vs are 0.33 and then 0.43 respectively. Right. So for this, so let's see. Uh, so beta Vx is equal to 0.43 and then beta Vy is equal to 0.33. So we have that. So here we need to look at the beams. Let me just go back here, copy this. I don't know why my copy is not working. Okay, so I think it should show. All right. So this is what I have. Just so that we don't have to be going all the way up here. Now we are looking at this. Oops, we're looking at this beam. Sorry, this slab in the space. All right. So we need to look at the support, which are the beams, right? So we look at beam B23. So that would be the beam right here. Okay. So let's look at beam 23 and beam C3 will be the same, all right, because it's continuous, right? So I can state that, let's look at the design loads on B 23 and C23. All right. So the maximum shear forces or the design loads on these ones would be so then and then also look at the design loads on these other these other beams right here. So these are let's say 2B, 2, 2B. So like I said, beam on 2BC and then 3BC. All right. So the BC, so the one that is perpendicular in the way to your short span becomes the VX. All right. So let me quickly do that. Let's take this over here, bring it here for now. Oops. So that I just have to do this. Okay. So here for this, my VSX will be here, which will be 0.43 times n, which is 14.2, and then our Lx is 5. So this will give us 30.5 kilonewtons per meter. All right, again, we are dealing with per meter width. So Vxy will be 0.033, no, 0.33, sorry, times 14.2 times 5, and that will be, I think 23, 23, oops, 23.4 kilonewtons per meter. All right. So let's look at the shear stresses. So let's start with the VSX. So the shear stress. So everything is just like whatever we did in with the beams when we were looking at the shear. So the maximum shear stress V will be equal to VSX over BD. Okay. And this will be 30.5 times 10 exponent 3 over the B is 1,000, okay, times a D of 150. And this will give us 0.2 newtons per millimeter squared. Okay. So we can now let's find the design the compressive or the concrete design stress, which is V sub C. And to find V sub C, we need to again go back to our previous tables, and then you would realize that we can look at to do that. When to find VC, we need to find 100 AS over BD. Okay, 100 AS over BD will be equal to 100 times the AS is 314. We know the area of steel coming to that side to 314, and then the B again is 1,000 because it's slab. We always assume a 1 meter length. Then times 150. Okay, so this should give us 0.21. Then the table that we had earlier, let me just see if I can find it. The table for shear stress. Let me see. So I have to go all the way to shear stress in beams, and I come up with that table. Hopefully, I can find it quickly enough. Mhm. So I think, yeah, great. So there's a table I was looking for. Um, I think this table should help. Sorry. Table 3.11, there should be something I'm looking for. Okay, so once we have this table, our 100 over ASPD will be somewhere in between. So somewhere in between this and that, right? And then we are looking at 150, so we are looking at these two sets of values. All right. So let's assume, for assumption, let's assume that, okay, our VC is 0.51. I mean, it's less than 0.51 anyways, all right? It's around 0. Maybe 5049. All right. So if your VC is 0.51, now your V is 0.2. Okay. VC, VC, so VC is more than V. All right. So since VC is more than V, it means that no shear reinforcement needed or required. Okay. And mostly the reason we don't really check for it because usually when you have the depth of your slab being less than 200 millimeters, most likely your VC would be more than the V. All right. And then that means that there will not be any need for shear. All right. So we can do that for all the different computations, the other one, and we'll still arrive at the same answer. Okay. So I think we are done with shear, we've done with the bending. The next thing is to look at deflections. All right. So I'll just discuss deflections in as a whole to cover a few things. All right. So usually this is what we do. All right. So normally when you're looking at deflections, pretty much you are okay, comparing actual deflections coming from the loads, uh, from loads, and then you compare these um, two limiting deflections. All right. The actual deflections from the loads or the actual member deflections, which is as a result of the load, should not exceed that of the limiting deflections. Okay. And that's basically what we have been looking at. All right. So um, in theory of structures, structure analysis, and all of that, you would calculate deflections. All right. And that's how we do it. So depending on the loading, the member support conditions, and all of that. So for example, if this is a simply supported structure and you have a UDL on its W, and this is your length L, then the maximum deflection which would occur at midspan would be 5WL4 over E, 584 EI. Okay, so that's for UDL. If it were simply supported, then let's say again with a point load P at midspan, this is L, then your maximum deflection is PL cube over 48 EI. All right. So normally you compare these deflections to what the limiting. So the code would have some limits, right? The code will have some limits, and some examples of the limits could be maybe span over 360, depending on what materials your ceiling or your floor might be made up of. You can also have a span over 250 and all of that. Okay. So the span is the length, and the span is normally in millimeters. So span is supposed to be in millimeters. Okay. So when you find this ratio, span over 360, and you compare that to the deflection, then you see your limiting deflection should always be more than the actual deflection to ensure that your structure is safe. Okay. If it's continuous, if it's a continuous beam or slab or whatever, the equations for the maximum deflections are going to change. Okay. And normally when we are calculating deflections, we prefer to use the loads that we use here is the unfactored live loads. Okay, normally, right? Or usually is unfactored live loads or the imposed loads, the unfactored imposed loads. So in this case, our loss was 4 kilonewtons per meter squared. Okay. We need to maintain that. Either we use that 4 as in for the slab, or as we were designing a beam, would have converted that area load into a UDL or into a line load and use them, but it will not multiply it by the 1.6, and it's only going to be the live load or the imposed load. Okay. So that's something to take note of when looking at deflections. Okay. Um, the other thing to do, or which we have been doing for some time now, is that one of the ways we can also check deflections is to use we check deflections by using the span to effective. I mean, the ratios between the two. All right. And normally, in this case, we look at it in the shorter span because of the fact that that's where the higher D value would be. All right. So take a note. So let's calculate the actual ratio. So let's say the actual span over effective depth. Okay. So the span for the shorter side will be the 5 meters. All right. So that's 5,000 divided by effective depth of 150. So this will give you, also give us 33.3. And we need to compare these to the limiting span to depth ratio. All right. I think I don't know if I remember mentioning an equation that we could use those times. But I think maybe this is the best time to bring that up, and then you could look at it. Okay. Oops. Okay. So we need to find the permissible or the limiting span to effective depth. Okay. And usually we so we go into the table. See where I can find this table. We've done this before. I don't want to spend too much time, but let me just look for the table and bring it back to refresh our memory. Where would this table be? I think I found the table. All right. Oops. So we have this table, right? And it says that this is for the basic ratio, all right? This is for the basic ratio. And since we are looking at continuous system, then our basic ratio is 26. Okay. So basically we need to multiply the basic ratio by the modification factor. Okay, which is what we've been doing. Okay. So with the modification factor, we can again go through tables. We go through tables, we find m over bd squared. So we have all these. I'm just going to bring the table up again, but then I'm going to use an equation to solve it so that we have that as well, right? So we have these tables. Also, we find our m over bd squared. Then we find our surface stresses. So this is supposed to be our surface stress Fs. And then once we find our surface stress, this is like Fy is equal to 500. If Fy is some other value, there's a way to calculate the surface stress straight away. And once we find the surface stress, and then and we know our m over bd squared, we can determine what our modification factor would be. All right, that we have done. The other option would be to use an equation. All right. So the equation would be when finding our surface stress. Okay, so this will be equal to, so that's a surface stress Fs will be equal to 5 over 8 uh, Fy times the AS required over the AS provided. Okay, so this 5 over 8, our Fy is 460. Great. Then for that particular, since we are dealing with pretty much MSXP, because that's where we'll find the maximum bending, mostly is going to occur um, at a mid-span, right? So if you go back to those calculations for the, where was it? For this, the mid-span, is that what I had? So I had 229, let's say 230. So let's see, I had 230. All right, for my AS calculated. And then the 262 was what I provided. All right. All the, yeah. So I could just come in here to this calculations all the way down here and go like my AS required was was 230, and then the AS provided was 262. So quickly we can find that 5 divided by 8 times 460 times, let's say, 230 divided by 262, and that gives us roughly about 252, okay, which makes sense, right? So around, let's see, 252 newtons per millimeter squared. Okay. So once we have that, our modification factor, most of these tables are base of equations, all right? So this becomes 0.55 plus 477 minus the service stress divided by 120 times 0.9 plus our MSXP over BD squared. So that's how the table is formulated, okay? So here we'll end up with 0.55 plus 477 minus 252, then 120, 0.9 plus our MSXP, I think we have 13.1 times 10 exponent 6 divided by 10, 10 exponent 3, which is the, or let me just say 1,000, all right, so I don't have to. So it's 1,000 for the width of the slab times 150 squared. So this is the equation. It looks kind of long, but it's fine. Let me just rewrite some of the items. Okay. So if we do that, we'll get, hopefully I'm correct. We should get 1.81. Okay. So assuming we haven't going with the 250, let's have an idea of to see if everything will look. I don't know what m over b d squared would be, but let's say 13.1, that's an exponent 6 divided by 1,000 times 150 squared will give us 0.58, so somewhere around here. So yeah, so we are close. We are somewhere close. I mean, yeah, it makes sense. All right. So we get 1.81 as our modification factor. So I could come in here and then I would have, so this becomes 26 times 1.81. Okay. And this is equal to 47. Okay. So we have to compare these two values, the actual and then the permissible. All right. So since permissible is more than actual, it means that we are okay. All right. So we've checked everything. Everything is fine. Now the next thing will be to check to draw our, or to sketch our, what's the name? Um, to sketch our reinforcement arrangement. All right. So let's see how to get that one done. Okay. So I'm going to just draw. Um, Let me draw the shape. I need some help. Okay, so let me use a ruler to draw the wrists. So again, let's go. Okay, what just happened? All right, so this is pretty much like a plan view of our section, and let's see what we need to do. Uh, so let's first look at the support. Okay, so let's look at the mid span. I'll try and use different colors so that at least we see how. So the mid span one, the first one, which is the mid span X, it's usually along the length, the shorter, or it's parallel to the shorter span. Okay. So let's say I have this. Let me. Usually we try to do our arrangement to go a little bit beyond. So let me do this. No, not this color. This color is not the best. I'll need to have a. Okay, so let's start with this. Let me make it thicker a little bit. All right. So this would be our try and take my time so that it makes sense to us. I'll run out of colors very soon. I'm pretty sure. That's fine. So this one right here. So it starts. Um, but if I'm to, okay, let me just do this. Sometimes this thing takes, okay. So here, I write with this. Oops, no, I don't want this case. Okay, great. So here, it says T10 at 300. All right. So this will be B1. All right. So this is for the MSXP. All right. If you want to know how many there are, we know the length. I think the length is 7 meters. So 7,000 divided by 300, and then that should give us what 20, I think roughly about 23. So this is 23 of them, right? Even though it's going to be less than because you have to subtract the extra. If you know the width of the beam, you take that one away from the span, the clear span, and then you can find how many you need. All right. Now the next one will be, so this is, I'll put this into brackets. Okay. I mean, we don't do that, but this is for the MXP. But we don't usually do that. Okay, we don't have that in there. So please take a note. It's just so that we know what we are dealing with. The next one will be the midspan. So the midspan we have so that'll be the MSYP. All right. So for the MSYP, here we are. Okay. And let me also draw that over here. Okay. So it starts right here. Okay, this is where it starts, and this is where it ends. Okay, it doesn't go beyond the support, and this shows that I think it's better to use this rather. Okay, and then this one. Okay, so that at least we know what we are dealing with. So here too would be if I'm to label it nicely, this is gonna be again. So this is T10 at 300, B2, and there'll be 17 of them if we do the math. Okay. There'll be 17 of them if we do the math. Okay. Okay. So this, I'm done with the bottom rebar arrangements. All right. Now the next one will be to do the top ones. And the top ones are typically over the support, right? Yeah, so I knew I was going to run out of colors, which I think I have. Um, okay, let me see what I can do. Maybe I can mix up. So this one is for the MSY positive. Let me see. Try to figure out what colors to use next. Same thing. Okay. Okay, let's work with this. This should be fine. All right. So the next thing would be to look at these. Oops, sorry. All right, so I think I forgot to do the bar mark. Let me just do bar mark so at least the whole thing is complete. Okay, so here, this will be bar mark, let's say 0, 1. This will be B1. I hope my thing is looking great. Um, sorry. Um, okay, so sorry, what am I doing? Let me get this, oops. So change the color back to what I had, okay. So T10 with a bar mark of 0, 1 at 300 B1. Let me do it. This is the better approach. At least the one I'm used to. So here, so this one will be T10, bar mark 0, 2. Then there are 17 of them. All right, so I think this should work. Okay. Now let's look at the over the support. And then for that, we would have, let me draw that over here. So I have this, so that one goes, oops, I need a thicker. Okay, so this one goes over the support. Something this, so the same thing over here for the support. Yeah, I know the lengths are slightly different, but the idea is the same. And then let me go with this now. Okay. So it would also start from here. No, I don't want that. Let me reduce the thickness of this. Okay, so it starts somewhere here to this. So it starts here and it ends over here. Okay. And the same will apply to the one here too. Okay, yeah. So they start here and end over there. Okay, so let me just stretch things a little bit. Too many things happening. Okay. So this, let me just show how they're connected. So this is a connection. So they both are the same. And this one was the one that gave us the T. So this one we had T. There was it T10. So let's say maybe this is bar mark, maybe bar mark 3 or something. Okay, I think this was bar mark 4. It's fine. Let me just do it bar mark 4. 04 at 250. Okay, so this is a T1, what we had earlier. And then how many would there be? If we divide 250, so let's say roughly about 7,000 divided by 250, and that'll give you about 28. So this is 28. And the same thing will also be here, 28 T10 bar mark 04 at 250 T1. Okay. So now we know where it starts and then where it ends. So it ends right here. I'm shading because I want you guys to see, not because we shade, all right? Just so that we can differentiate between where the line starts and then where it ends. Okay, all right. So the next one is to do for the secondary top bar, and I'll need another color to achieve that. Hopefully I can get one that would work. Uh, so let me go with the gray. Hopefully it works. All right. Let's go with the gray. And that one would be So it's going to be somewhere along this length. Oh, the gray works nicely. All right, so this is going to be for that one. All right, so whatever we have on the left will be the same on the right. Okay. So let me just show you how this will also start right here and then end over here. It starts and end right here, and the same applies to this guy too. Okay. Yeah, so let me shade so that we know the indicator lines from the river. Okay. So again, to make things interesting, let me rather extend this one up here and then this one up here. Okay. Oops. Things have shifted for whatever reason, I don't know. Okay. So with this one, it would be T. So this would be, oops, let me reduce the size. So here, this would be T. I think there'll be how many of them? If you do the math, you should get about 17 also. So there'll be 17 T10. Let's say bar max 03 at 300 T2. So again, here is 17 T10 bar max 3 at 300 T2. All right. So this is in plan. This is how the rebar arrangement would be. All right. So we can take cross sections of it and just see how they would look like. So let's take some cross sections. Let's just take a section through here, another section through here. Um, so this is section maybe BB. Section, let's call this section here section AA. Okay. So with section AA, this is how our structure would look like. I'm just gonna draw that by hand. All right, too many rulers tied. Okay, so we have maybe this may help. Let's see. Let me just go ahead and just draw this. Okay, so maybe this should help. Okay, great. And then I have so down here. Oops, let me just. So we have something like this. Yeah, I know. It looks strange. So this is section AA. So at least I've labeled my bar mark nicely so we can easily draw. So with section AA, this is not the best that I can have it to look like. So I'm going to use the colors as I use so that it helps us to appreciate what is happening. All right. So the red would be the B one. So the red will be right on top like that. Okay, let me increase the thickness. So the red will be right here. Okay. Then the purple would be the ones running below. Okay, like this. This is for the bottom. All right. So basically, this is I think I named this one bar mark 1. So this is bar mark 0, 1, and then this here is bar mark 0, 2. Okay. All right. Then at where the supports are, maybe I have to move this one up. Can I move it up a little? I think I can. Okay, great. So here, um, so this is for section oh this PC. All right, so let's look at it. The So I'm going to do the T2. Okay, so the T2 is the ash colored one. So the T2 is the ash one. So that would so this is the ash. It's not thick enough. So this is the ash colored one right here, and this is how far it goes for the T2. Okay, then on top of it, you have your T1s. Okay, and then so the T1s will be the orange colored ones. So then the T1s will be somewhere here. And let me add one more here. So, whoops. Then extend the hash a little bit. Okay. All right. So that here you would have, in terms of the labeling, this here and this here will be different. So the ashes, which one? The ashes 03, and then this one is what I just draw. Okay, let me go back. Okay, I don't know what happened. Oops, I think so many things. Okay, so then the ash is 03, and then this is 04. So this is section A. A. Okay. Now we can take this whole thing and draw section BB. All right. If we want to, pretty much with section AA, um, this is green line B, this is green line C. All right. Then, so I can take this whole thing. Let me see if I can. Okay, I think I can. I'm just gonna sprinkle some magic dust and see what happens to it. So I'm going to make this one section BB. Let's see what happens. So section BB, section BB, I'll have 2 and 3. So maybe I can make this one 2 and make here 3. And then move these guys up. Yep. Then move this one up. And then move this one to also. Yeah, I know. Just trying to be lazy, but I'll just do the rest. All right, so take this guy away. Don't need you. Don't need you. And then maybe just bring these guys down a little bit. So it's just rearranging in the sense that it depends on where you are standing and what you can see. All right. So I have to change colors slightly. Just give me a second. This whole thing would have to be No, purple. I'll just change the colors. But let me just pause, do the changes, and then I'll come back. All right, so this is how the section BB will look like. It's just standing at a different position and then viewing the section of the slab, right? So this is in this, we'll just make it simple terms how slab designs are done. And I think that should help us to look at, I mean, be able to design our slabs, especially slab panels. For the first time, when you move for the first time, uh, levels, but after a while, you see that the steps keep repeating, and then that's all there is to it. So, okay, all right. So this will bring us to the end of the second part of the lecture 9. Then we'll see ourselves